Today we're going to move into a different part of trigonometry. Last time we talked about right triangle trigonometry. Today we are going to be talking about trigonometric identities. This is something that's very different. It is something that's brand new and it takes a little bit of time to get used to and to get good at. Before we get into that, the first thing I'm going to talk about are trig values of special right triangles. Now you may remember special right triangles when you were taking geometry, the 30, 60, 90 triangle, the 45, 45, 90 triangle, and that there were special ratios that went along with each of those triangles. For the 30, 60, 90 triangle, we know that so I've simplified this here to say if the shorter side is 1, then we know that the longer side is going to be root 3 times 1, and we know that the hypotenuse is going to be twice the shorter leg. So it's always in this ratio. So you may have learned it as x root 3, and 2x. And here I've just simplified it down so that we can just work with a triangle, a 30, 60, 90 triangle, where the shorter leg is 1. In the 45, 45, 90 triangle, this is an isosceles right triangle. So we know that if one of these legs is 1, we know the other leg must also be 1. So they're always equal to each other. And then the hypotenuse is always root 2 times the length of one of those legs. Again, here I've simplified it so that we're just working with 1, and root 2, rather than maybe what you had remembered in the past, x, and x root 2. Okay, so we're going to fill in this table here. So along the top, we have the 30-degree angle, 45-degree angle, then the 60-degree angle, so we're increasing. And then on the side over here, the sine, cosine, and tangent of each of those angles. And we can get all of these from the triangles that we have on the right there. So sine of 30, that's equal to the opposite over the hypotenuse. So opposite the 30-degree angle is 1, and the hypotenuse is 2. So that's 1/2. You can do the same thing with cosine of 30. The adjacent side is root 3, and the hypotenuse is 2. And then tangent of 30, this is going to be the opposite over the adjacent, so 1 over root 3. Now if you rationalize that denominator, meaning if you multiply top and bottom by root 3 over root 3, you end up with root 3 over 3. Let's skip over to the 60-degree angle while we're looking at the 30, 60, 90 triangle. And now, across from the 60-degree angle, the opposite side is root 3, the hypotenuse is 2, so this is root 3 over 2. Cosine, that would be 1 over 2. And then the tangent is opposite over adjacent, so root 3 over 1, or just root 3. Okay, now let's look at the 45, 45, 90 triangle. So for sine, it doesn't really matter which angle you're looking at, because they're both 45-degree angles. The opposite and the adjacent side are both 1. So the opposite is 1 over the hypotenuse, which is root 2. Rationalize that denominator, and we have root 2 over 2. Cosine, same thing. The adjacent side is 1, and the hypotenuse is root 2. Rationalize that, we get root 2 over 2. And then tangent is opposite over adjacent. That would be 1 over 1, or just 1. Now this table is very useful, particularly when you get to calculus. It is best if you are able to memorize this. So for this class, you will be expected to memorize this table. Now, try to find some sort of pattern to help you memorize it. What I don't want you to have to do is to have to draw out the triangles and derive each of those ratios every single time. Now, if you remember it as 30, 45, and 60 going across up at the top, and as you're going down, sine, cosine, and tangent, say you were looking at that first row for sine. Notice how they're all over 2. And then notice in the numerator, it goes 1, root 2, root 3. So you can imagine it's really just going up, 1, 2, 3. Just remember the square roots. For a cosine, it goes just the opposite, root 3, root 2, then 1, and they're all over 2. And then for tangent, one way you can, it might help you, is you can take sine and cosine, and you can divide the numerators. So for 30 degrees, tangent of 30 degrees, we can take the 1 in the sine of 30 and the root 3 in the cosine of 30 and divide them. And that gives us 1 over root 3, which is root 3 over 3. Same with the next one. Root 2 divided by root 2 is 1. And then in the last one, root 3 divided by 1 is root 3. That's probably the most in terms of patterns that we can find that might be helpful to help you memorize that table, but hopefully you don't need to quite so forcefully remember this one is this one is this, but maybe a pattern in there can help you remember it a little bit better. Okay, next we're going to talk about the trigonometric identities, getting more into the most of what we're going to be talking about today. So there are 3 groups of identities that we're going to talk about today. There are more groups of identities that we'll continue with in the next lesson. So today we're going to talk about the reciprocal identities, the quotient identities, and the Pythagorean identities. So we'll start with the reciprocal identities. So these, as their name suggests, has to do with the pairing of the reciprocal trig functions. So remember that sine is the reciprocal of cosecant. So sine of x is equal to 1 over cosecant of x. Cosine is the reciprocal of secant. So cosine of x is equal to 1 over secant of x, and vice versa. And then tangent of x is equal to 1 over cotangent of x. And the same thing the other way. So cotangent of x is equal to 1 over tangent of x. Now once you know the pairings of sine going with cosecant, cosine with secant, and tangent with cotangent, then you'll be able to pretty easily come up with these reciprocal identities. Next are the quotient identities. So with these, there are only 2. And the first is tangent of x is equal to sine of x over cosine of x. And the second one is just the reciprocal of tangent. The reciprocal of tangent is cotangent. So cotangent of x is equal to cosine of x over sine of x. Lastly, we have the Pythagorean identities. As the name suggests, if you remember, the Pythagorean theorem was always the sum of squares equaling another square. So that's what you're going to see here. So the first one, there are 3 of them. The first one is sine squared of x plus cosine squared x is equal to 1. Now just as a note, in terms of notation here, when we write sine squared x, really it means it's not just sine that's being squared, because sine itself is just a function, right? It's not an actual value. But we don't want to write it as sine x squared, otherwise it looks like it's the x being squared. So the notation here, sine squared x, is really the same as if you were to write sine of x in parentheses, and then you were to square the entire thing. Now this is just kind of a shorter way to write it. Instead of having to write the parentheses, a shorter way to write it would be sine squared x. In calculus, you may find it helpful to, in some cases, particularly as you're taking derivatives, it might end up being helpful to write sine of x, the entire thing, in parentheses, and then square that entire function. So both are perfectly acceptable ways to write sine squared. So either put the squared on sine or put the squared on the entire thing in parentheses. But what you don't want to do is you don't want to write sine x squared. Otherwise it looks like it's the x being squared before you take the sine of that value. Okay, so there are 2 more Pythagorean identities. The next one is 1 plus cotangent squared is equal to cosecant squared. And then the last one is tan squared plus 1 equals secant squared. Now, for these identities, you do need to have them memorized. Now, I'm not necessarily going to ask you to list off all the identities, but you memorize them because what we are going to be doing is we are going to use these identities in proofs. And the only way you're going to be able to use them in proofs is if you know the identities already. Now, I know you're just learning these now, so feel free to go back and forth for the time being, but the more practice you get, you'll notice that the more you're actually just naturally memorizing the identities. So let's talk about how we use these identities in proofs. So generally in proofs, you're told what you're trying to prove. So what you want to do is you're told, prove that this statement is true. So you're going to start with one side of the equation and show that it will turn into the other side of the equation. Okay, so pick one of the sides. It doesn't matter if it's the right or the left. Generally, I like to pick the side that's more complicated and try to simplify it until it looks like the other side. Now, what I do not want you to do, what you cannot do if you're trying to prove something, is you do not want to do something to both sides. What you want to do is you want to pick one side, you know what you're trying to get to at the end, and what you're going to do is you're going to do anything you can to that one side until you get the other side. Now, things that you can do, aside from just simply using the identities, is you can multiply by 1, so anything that's in the form of 1. So if somehow multiplying something by sine over sine is helpful, that's multiplying by 1. And you can replace or substitute using identities. Now, one thing you do want to do for these proofs is you always want to give a reason for each step. Okay, we're going to do some examples here. Start with a simpler one. This says, prove that cosine theta times secant theta is equal to 1. Okay, so pick one of the sides to start with. Again, I like to start with the side that's more complex, in this case, the left-hand side. Now, in terms of a reason to start with this, what do you normally start with when you're starting a proof and the first step is what? It's given to you. Now for the next step, now remember we're trying to make this look like the other side. So we want to see if there are any identities that we can use that might help us simplify this side down. So you might notice that cosine and secant, remember those are reciprocals of each other. So one thing you can do is you can substitute the secant of theta with 1 over cosine theta. You can also change cosine theta to be 1 over secant of theta. Either way is fine. So another thing you'll notice is that for proofs, there will be multiple ways of going about proving something. So for our reason here, we want to say that we're using a reciprocal identity. Okay, so from here, the next thing we do is we multiply that. We get cosine over cosine. We can just say that's multiplication. And then if we simplify that, we get cosine divided by cosine is equal to 1, and that's just simplifying it. And so you'll notice that the first step was one side, and the last step there is the other side. So we've successfully proved that this is true. Let's take a look at example 2. Prove that secant theta plus tan theta, in parentheses, times secant theta minus tan theta, in parentheses, equals 1. Okay, it looks like the left-hand side is the side that's more complex, so let's start with that, and that's given. Now for a problem that has things in parentheses, and on the other side I notice it's very, very simplified, what I'm going to do is I'm going to start by multiplying everything out. Now this is going to make it seem more complex, but it will help us to simplify the problem. So multiplying this out, we have secant squared minus secant times tan plus tan times secant minus tan squared. And it looks like those two terms in the middle, the minus secant tan plus secant tan, will cancel. Okay, so that comes out to be secant squared minus tangent squared, and that's just simplifying. Okay, but we're still not at the stage where we have it equal to 1. Now, if you do see functions that are squared, that should make you think, oh, maybe I could use a Pythagorean identity to help us out here. Now, for the Pythagorean identities, we see that there is a relationship between secant squared and tan squared, and that's that secant squared is equal to tan squared plus 1. Now, I know some of you might want to rearrange the identity itself. Let's try to avoid that. Let's try to avoid changing the identity, but instead let's use the identity the way it is and substitute. So since we know secant squared is equal to tan squared plus 1, I'm going to replace the secant squared in here with tan squared plus 1. That way I'm not changing the Pythagorean identity the way it's been presented to us. Now, once we've done that, you can see that the tan squared and the minus tan squared will cancel, and that leaves us with 1. So after some simplifying here, this is equal to 1, which is what we have on the right-hand side. So again, we started with the left-hand side, and we were able to show that this is equal to the right-hand side, because that's the last step. That's what we showed it is equal to at the end.